Welcome to Senior Plasma Physics, Lecture 1. As with most of the course, we follow closely the textbook by Francis Chen, An Introduction to Plasma Physics, Volume 1. This lecture is contained within Chapter 1 of that textbook. We'll start off by giving a basic definition of a plasma and give some examples. We then need to define the temperature as it applies to a plasma. Finally, we need to talk about the type of electrostatic shielding that occurs within a plasma known as Debye shielding and how this can be used in obtaining more quantifiable criteria for the definition of a plasma. So how do we define what a plasma is? In short, you can say it's an ionized gas, but that's not a completely correct answer, since there are some ionized gases that are not plasmas. By the end of this lecture, we'll present criteria that helps to distinguish between those two situations. But you don't just need a gas to form a plasma. You can form a plasma from all three states of matter: solids, liquids, or gases. You just need the right amount of energy added to a system, such as heat. But there are many ways to impart energy to these states of matter to form a plasma, as we'll see throughout this course. A plasma can be fully or partially ionized. So what does that mean? A fully ionized plasma means that 100% of the atoms are ionized. By implication, a partially ionized plasma isn't. Only a fraction of atoms are ionized. That means the fully ionized plasma only consists of ions and electrons, while the partially ionized plasma not only consists of ions and electrons, but also of neutral atoms and molecules. A list of examples of plasmas can be quite long, but here are some examples. Our sun is a plasma. Any sun is a plasma. The interstellar medium, fluorescent lighting, lightning, and the list goes on. I'm sure there are many examples that you can think of. One of the main parameters of a plasma is its temperature. The collisions between the particles in a plasma behave classically. That means they follow Boltzmann statistics. The result is that you end up with a distribution of speeds known as a Maxwell-Boltzmann distribution. For short, we call it a Maxwellian. The expression for the Maxwellian is given by this. Most of the variables there follow standard notation, but here are some definitions. V is the speed of the particles. N is the number density, that is, the number of particles per unit volume. This is another main parameter in plasmas. M is the mass of the particles. K subscript B is the Boltzmann's constant. But the important parameter in this equation is T, the temperature. So what if you didn't have a Maxwellian distribution of velocities? Then you can't really talk about a temperature. You may say talk about an average energy. A temperature following Boltzmann statistics is the parameter that appears in the Maxwell-Boltzmann distribution. In the same way, temperature is defined for quantum systems depending on whether you had a Fermi-Dirac distribution or a Bose-Einstein distribution. The meaning of the function f of v is not obvious. It doesn't just mean the number of particles, although the number of particles can be derived from it. We're going to leave the discussion about what this means until we cover the kinetic theory part of the course. A plot of the Maxwellian is given by this for two temperatures, 1000 and 5000 Kelvin. Notice how the peak in the distribution goes to higher velocities with increasing temperature, as you might expect. It should be straightforward using calculus to obtain the speed at the peak, Vp. However, the average of the squares of the speeds, known as root mean square speed, is not so straightforward. You need to know more about the meaning of the Maxwellian in order to derive the expression for the root mean squared speed. Plasmas can have temperatures in the thousands and millions of degrees, so it becomes inconvenient to keep talking about the temperatures in those units. It's much more convenient to express the units in electron volts. Here is an example of how this is done. Assume we want to convert room temperature at 300 Kelvin 2 electron volts. We substitute the temperature, T, in this expression and obtain 0.026 electron volts. But plasma temperatures aren't really usually that low. Quite often they're much higher than that. So I'll leave it as an exercise for you to show that a 1 electron volt temperature is equal to 11,600 Kelvin. A plasma is made up of free charges, both negative and positive. So you can imagine if we insert in the plasma 2 oppositely charged conducting spheres. The negative charges and the positive charges will move to the spheres of opposite polarity to essentially shield the electrostatic potential from the spheres. This complete shielding of the charged spheres will only occur if the free charges don't have sufficient kinetic energy to overcome the attractive potential energy of the spheres. But as we've seen from the Maxwellian distribution of velocities, that there are always charged particles in the high velocity tail of the distribution that have a sufficient energy that is greater than the attractive electrostatic potential energy to basically leave. And so the shielding around the sphere is inherently incomplete. But we do introduce a length in the plasma whereby most of the charge is contained. This is known as the Debye length. The symbols in this expression are as usual, but it's important to comment on one particular parameter, the density. This is the density at a much greater distance than the Debye length, because the density within the Debye length does change. So within a Debye length, changes in the electric potential can be measured. It doesn't mean that changes in the potential outside the Debye length can't be measured, because as we said, the shielding is not complete, but the changes are much smaller. Quite often we do treat this Debye length as a kind of a boundary, but it's not really a boundary, as we will show in later lectures when we derive the Debye length. It's important to note that there is nothing special about the introduction of metal spheres. They basically represent an electrostatic perturbation of the plasma. The perturbation doesn't have to be from a physical object, although it can be. It can be, say, from electromagnetic radiation passing through the plasma. When we started this lecture, we gave a very simplistic answer to what a plasma is. But there are actually quantifiable criteria that determine if an ionized gas is a plasma or not. Plasmas must be macroscopically charge neutral, also called quasi-neutrality. There are, however, plasmas that are called non-neutral plasmas, but we'll stick with the definition followed by Chen, that is, of quasi-neutrality. That means the total negative charge is equal to the total positive charge in the plasma. This can be obtained by the following expression, where the left-hand expression is the total negative charge and the right-hand expression is the total positive charge. Plasmas must also show collective behavior. What does that mean? It just means that the electromagnetic forces in the plasma dominate over normal hydrodynamics you might get in a gas. So how do we quantify these criteria? Quasi-neutrality requires that the dimensions of a plasma, L say, are much greater than the Debye length. Otherwise, as you've seen from our metal spheres example, that there will be a space charge within the Debye length. Obviously, to have collective effects, we need to be dealing with a large number of particles. So we end up introducing something called a Debye sphere. A Debye sphere is an imaginary sphere that has a radius of 1 Debye length. So we want the number of charged particles in a Debye sphere, Nd, to be much greater than 1, and is given by this expression, where we're basically multiplying the volume of the charged sphere with the number density of the charges. In this case, it's the number density of electrons.